Hi once again. We are still discussing indeterminate forms of limits. In this second part, we're going to approach certain alternative methods to factoring and canceling. Strategy number 2 will involve rationalization. This strategy is particularly useful when 0 over 0 forms occur in the presence of square roots. As opposed to polynomials where factoring is easy, square roots may require some more elaborate techniques in order to find common factors. Square roots cannot be factored like polynomials. The rationalizing process or the rationalization process will make the algebra of finding common factors more manageable. Be careful not to apply the factor theorem, as it does not apply to radicals. So remember that from our review topics, rationalization requires that we use the conjugate of a term. Here are the list of mutual conjugate expressions. So for an addition of a term plus a root, the conjugate would be the term minus the root. The addition of a root plus a term can be, there's a conjugate for it, which will be the root minus the number b, and if you have the sum of two square roots, then the difference between these square roots will act as the conjugate. For example, let's evaluate the limit as x approaches 1 for the quotient 2x minus the root of x plus 3 over x squared minus 1. As usual, we would attempt direct substitution before thinking of using any methods to find this limit. So quick calculation will give us 0 at both numerator and denominator when x is replaced by 1. So direct substitution leads to the indeterminate form 0 over 0, which requires that we do some special techniques in order to find whether or not this answer is definite. So we would expect x minus 1 to be a common factor of both the numerator and the denominator, but 2x minus root of x plus 3 is not easily factored. So here is where we're going to make use of the rationalization process. The sum of 2x with the root of x plus 3 is the conjugate of 2x minus the root of x plus 3. You can notice that if we multiply above and below the two terms or the fraction that is involved in this limit, then we will not cheat. We won't alter the value of the function we are evaluating. At the numerator, you will want to expand these terms because 2x plus root of x plus 3 was purposely chosen to be the conjugate of 2x minus root of x plus 3. At the denominator, you don't want to expand because x squared minus 1 and 2x plus root of x plus 3 are not mutual conjugates. So you will just make things worse by expanding. If you expand the numerator, you will find 4x squared minus x plus 3. I'm going to go back to the previous slide to justify this outcome. Do you notice that at the numerator we have a difference of squares, a minus b, a plus b, and therefore a squared minus b squared will be the outcome of that expanded form at the numerator. And that's how 4x squared minus x plus 3 is obtained. The parentheses are necessary because we are subtracting the entire outcome of root of x plus 3 squared. At the bottom, you'll notice that no expansion took place. The two terms are left simply side by side. At the numerator, we can then distribute the signs, and then the factor x minus 1 can be identified because the numerator is now a polynomial, which is more easily factorable, and at the bottom, x squared minus 1 is a difference of squares. Canceling the common factors leads us to a result for which direct substitution can now be applied, and we're going to get 7 over 8. So really, rationalization is necessary in order to generate polynomials that we can then factor. Strategy number 3 is to simplify fractions. So occasionally, a 0 over 0 form will occur when computing a limit that displays multiple fractions. Simplifications that will lead to more simple factoring and cancelling of terms could reveal to be a very efficient strategy. Here's an example where we have to evaluate x over 2 minus 2 over x divided by 4 minus 2x. As usual, a quick verification, a quick computation will show that the numerator and denominator are both 0 and x is equal to 2. So we are faced with an indeterminate form of type 0 over 0. Finding a common factor to simplify, again, most likely x minus 2 will be the factor we're going to have to look out for, since x going towards 2 is what's creating the 0 over 0 form that we have. Well, this will be more easily accomplished if the expression x over 2 minus 2 over x all divided by 4 minus 2x is simplified first. So we're going to find a simplified version of this expression. We could, of course, look to create common denominators and perhaps then flip the fractions because we would have a quotient of two fractions. But I would definitely suggest a way to remove all fractions instead. So rather than have to deal with them, we'll just simply find a way to remove the fractions. So what if we were to multiply our expression by 2x over 2x? Obviously, 2x over 2x is equal to 1 unless x is 0, and therefore will not alter the value of our rational function. Now look at why I'm making that choice. I'm making the choice of multiplying by 2x because 2 is the divider of the first term, x over 2, and x is the divider in the second term at the numerator, 2 over x. So if we were to multiply by 2x, that would, and distribute, this would eliminate both fractions at the same time. We're also multiplying by 2x at the bottom to guarantee the overall result is not changed. At the numerator, I'll expand because 2x was purposely chosen to simplify both fractions. At the bottom, no expansion is necessary because the bottom doesn't involve fractions. So here's the outcome after expanding, and again I'll take you back to the previous slide. X over 2 times 2x is 2x squared over 2, which is x squared, and 2 over x times 2x is 4x over x, which is 4. At the bottom, the terms have not been distributed, leaving them in factored form. You'll recognize the numerator to be a difference of squares, and at the denominator, you'll also recognize x minus 2 as being a factor hiding within 4 minus 2x. So by simple factoring and removing the minus 2 factor, x minus 2 is brought to light and can be then eliminated. So the simplified fraction that we get can then be reevaluated as x approaches 2, this time by direct substitution, to give a result of minus 1 over 2. Sometimes a limit may require that we combine strategies. In this example, we have the quotient of 1 minus 4 over x with 2 over root of x minus 1, where x is heading towards 4. Notice it's the same pattern every time. We would always try direct substitution first and foremost, and in this case we will get an indeterminate form of type 0 over 0 that involves both fractions and expressions that contain square roots. So just attracting your attention by using color here, we have a fraction where x is the divider at the top. We have a fraction where root of x is a divider at the bottom. So I'm going to choose to multiply by both x and root of x. That for sure will eliminate the denominator in both cases. At the numerator, I will expand the x to both 1 and 4 over x. At the denominator, I will expand root of x to both 2 over root of x and 1. You guys probably see why I'm making this choice. I'm expanding only what's necessary to cancel off the fractions. So here's where we are now. We've got a simplified fraction than we did when we started off with. But it is still a 0 over 0 form. And the bottom 0 involves a difference, 2 minus root of x, that probably requires some rationalization. So I've chosen to multiply by 2 plus root of x at the bottom to act as the conjugate of 2 minus root of x. I've multiplied above by 2 plus root of x to guarantee overall that we're not changing the expression whose limit we're calculating. You can probably guess where I'll expand and where I won't. So here is the outcome. Bringing you back to the previous slide, I've expanded the denominator. 2 minus root x times 2 plus root of x is a difference of squares. So if we think of that as a minus b times a plus b, an a squared minus b squared form will be obtained. So 4 minus root x squared, which is 4 minus x. At the numerator, no expansion would be necessary nor helpful. So all the terms simply appear to stay as they are. And now common factors are becoming more and more visible. Actually, all we need to do is factor a sign out from the denominator to clearly visualize the common x minus 4s, which can then be eliminated, and the ensuing simplified expression can be evaluated by direct substitution, which in this case would give minus 2.